Hello, my name is Elias Lind and I study the course in Artificial Vision and Pattern Recognition. I will take you through the paper on practical approach for detection and classification of traffic signs using convolutional neural networks. In this groundbreaking paper, the authors present a lightweight and accurate way of recognizing traffic signs using optimized convolutional neural networks. Traffic sign recognition is one of the major tasks in advanced driver assistance systems, ADAS, and is an indispensable part of autonomous cars and robot object recognition. The recognition of traffic signs is mainly done in two stages, including detection and classification. The detection module analyzes the image in order to locate patches that are only consisting of singular traffic signs. Next, the classification module analyzes each patch individually and classifies them into classes of traffic signs. The good thing about the characteristics of traffic signs is their design simplicity, which makes them easy to find and understand by both humans as well as artificial drivers. The fact that they are made up by simple shapes, such as circles, triangles, polygons, or rectangles, and composed of basic colors, such as red, green, blue, black, white, and yellow, and as basic pictograms or symbols that are communicating their meaning, makes them perfect targets for object recognition and classification. Even though the design is clear and discriminative for human drivers, there are challenging problems in real-world applications of computer object recognition, such as shadows, distance, weather condition, and age of signs that need to be addressed when it comes to the way artificial agents understand traffic signs. If the car is autonomous, it also needs to identify the signs, classify them, and react to them, all whilst moving and under time pressure. The common pipeline in recognizing objects is to extract some features for each object and train a module to classify them using the extracted features. Conventionally, features are extracted using handcrafted methods, where someone tells the system what features to look for. One problem with these handcrafted features is their limited representation power. This causes some classes of objects to overlap with other classes, which adversely affects the classification performance. One automated solution to this is to automatically teach a function to transform the image into a feature space in which classes are linearly separable, something a convolutional neural network or ConvNet is really good at. If you are not familiar with the workings of a convolutional neural network, here's how it works. There are four main operations to a ConvNet. Convolution. Convolution means extracting features from the input image. This usually involves moving a matrix, filter, or kernel over a picture to find its features. The output is a feature map that can consist of features like edge detection, smoothing, sharpening, or blurring. The more filters you use to build a feature map, the greater the depth of the map. Non-linearity. Since convolution is a linear practice, but most real-world pictures you'd like to classify are non-linear, you need to add non-linearity to the ConvNet. Something like a rectified linear unit, or ReLU, could be used and applied pixel by pixel to replace all negative pixels with zeros. This makes our linear convolution nonlinear, so that the network is learning something that it can use to actually classify the real-time data. Pooling or subsampling, also called downsizing, reduces the dimensionality of each feature map but retains the most important information. This could be done by max, average, sum, etc. In the case of max pooling, we're choosing the greatest pixel value from a, let's say, 2 times 2 matrix. This also reduces the dimension of the feature map. Pooling is good for reducing the number of parameters, making it more manageable and easier to compute, which also controls overfitting. It makes the network invariant to small transformation, and also makes our network be able to detect objects in an image no matter where they are located inside the image. Fourth and last, classification. The output of the convolution and the pooling layers represent high-level features of the input image. Fully connected layers use these features to classify the image into various classes based on the training dataset. It also combines these feature maps to see what it can learn from combining them. The ConvNet is then trained on training data and changes its filters and connection weights within the fully connected layers, depending on the annotations given in the training data. If the ConvNet had done some wrong classification, it learns that here and then changes its connection weights accordingly to make up for that. In many situations, ConvNets can classify images better than humans, and a ConvNet can now classify traffic signs better than human experts on datasets like German traffic sign benchmark. Despite this, some of the solutions are non-computationally effective and require a lot of computational power. Given the fact that an advanced driver assistance system has limited computational power, might not be online at all times, so that you can use online systems, and has to perform various tasks at the same time. This means that it's crucial that the detection and classification of traffic signs consumes as little processing power as possible. This article presents a new and more lightweight and optimized ConvNet for both detection and classification of traffic signs. This new approach is able to process 37.72 high-resolution images per second using a GeForce GTX 980 GPU with an average precision of 99.89%, which indicates a nearly perfect detector. Using the traffic signs, pictographs, and shape to classify the sign, this new method establishes a new record on classifying the German traffic sign benchmark dataset, being able to classify 99.55% of the test samples correctly. Compare this to earlier trials, this ConvNet uses less numbers of arithmetic operators and has better accuracy. Let me tell you how this works. A lightweight ConvNet is used to detect traffic signs using a real-time sliding window detector within the ConvNet. In this method, a bank of convolutional kernels are applied on an image, and the output of each kernel is individually aggregated. Then, the final feature is obtained by concatenating the aggregated values. The proposed ConvNet learns a bank of 60 convolutional filters each with a 9 times 9 times 3 coefficient. The output of the first convolutional layer is a 12 by 12 by 60 tensor, where each slice is a feature map, giving the system a depth of 60. Then, the aggregation is done by spatially dividing each feature map into 4 equal regions and finding the maximum response in each region. Finally, the extended feature vector is non-linearly transformed into a 300-dimensional space, where the ConvNet tries to linearly separate the two classes, traffic signs versus non-traffic signs, in this space. The detection process starts with sliding a 20 by 20 mask over the image and classifying that patch using the detection ComNet before moving on to the next patch. This is a time-consuming action, but can be done swiftly on a dedicated GPU like NVIDIA Drive PX. To make this process as fast as possible, the whole high-resolution image is transferred to the GPU memory and the detection is done on different patches simultaneously. The 20 by 20 image is turned into a 12 by 12 feature map for each kernel, and the max pooling layer then creates a 2 by 2 single feature map out of this result. Using a GeForce GTX 980 card, this setup can process 19 frames per second. For the classification, the detection ComNet is transformed for classification of traffic signs by replacing the color image with a grayscale image, removing the linear transformation layer, reducing the kernel size in all layers, adding one more fully connected layer, and replacing LRELU activation functions with PRELU activation functions, and then another fully connected layer is added to the network for flexibility, making them 3 in total. This makes it possible to classify 50 images in 3.5 milliseconds due to parallel architecture on the GPU. For the experimentation on the GTSRB, all the images go through the ComNets. To reduce the effects of overfitting and getting a too precise classification, 12 transformations are done on the image. These are everything from translation, smoothing, sharpening, histogram, equalizations, etc. The detection ComNet is first trained using ground truth bounding boxes and the negative samples collected randomly from the images. Then, a hard negative mining is performed on the training set in order to collect more organized negative samples, and the ComNet is trained again. Average precision of the sliding ComNet is 99.89%, which indicates a nearly perfect detector. This puts the precision of the sliding ComNet higher than handcrafted methods. To get rid of false positives, you use post-processes like having at least 10 bounding boxes detecting a region as a traffic sign for it to be deemed an actual traffic sign. In real applications, it is necessary to study stability of the ComNet against image degradations. Adding some Gaussian noise with a standard deviation of 1 sometimes causes the model to incorrectly classify the noisy image. And that is noise that is barely detectable to the human eye. However, admissible results are required with noise up to standard deviation of 10. Using these modifications, the time to completion of the classification ComNet was reduced compared with previous ComNets. The experiment in the paper on the German traffic sign recognition benchmark dataset showed that single classification ComNet is able to classify 99.55% of the test image correctly, and that is quite amazing. That has been my walkthrough of this paper. Thank you for listening and have a good day.